Hello, students. I'm in our nation's capital having fun with grandchildren, and now I want to talk with you about least squares. This is chapter 4.3 in the Strang book. Last time we talked about fitting a line to data points. Of course, if you just have two data points, you can fit a line perfectly to two data points. But if you have more than two data points and the points don't lie on one line, that is, they're not collinear, then you're going to wind up with a system of equations that has no solutions. And what you do is you project. So we have a system of the form ax equals b, and what we're going to do is we're going to project the b onto the column space of A, find the nearest point in the column space of A, the nearest vector in the column space of A, and use that instead of that B to get a solution to the system. That is the closest to the desired solution in the least square sense. Okay, so this time, but there's nothing saying we need to fit a line. We can fit a parabola. If we have these 4 points, any 3 points would define a parabola, but we have 4 points. So our general equation for a parabola is ax squared plus bx plus c. So when I put in a -1 in the x, I want to get out a 1. So if I put a -1 in for x, I would get a minus b minus c equals 1. If I put a 0 in for x, I would get a equals -1. If I put a 1 in for x, I would get a plus b plus c equals 0. If I put a 2 in for x, I would have a plus 2b plus 4c equals 2. So I want to be able to get an ABC, that those coefficients that are the best possible in the least square sense. So these equations give rise to this matrix system of equations, which has no solution. So we use our projection and we calculate A transpose A. So this is A, this is the matrix A. So I multiply A transpose A and I get that. I multiply A transpose B, where this is the B, and I get that. This system of equations I can solve. And my solution is -7/10, -3/5, and 1. So this is my best fitting parameter in the least squares, parabola in the least square sense. Okay, we can do that with cubics. If you have 4 points, a cubic is perfectly defined. If you have more than 4 points and they don't lie perfectly on a cubic function, then you're going to have a system with no solution. Okay, so this kind of thing can be done regardless of what system we have. Almost. If we're given an ax equals b, a system of equations where there's no solution, as long as these columns are independent, then we can apply this. A transpose A x equals A transpose B will have a solution, an x-hat solution. But if these columns are not independent, so they're actually not a basis for the column space, then we're in trouble. Then we've got to use an A that would only consist of the columns that are bases for the column space. Notice in this one, these are linearly independent, but there's another thing about them that's unusual, and that is, if you do the dot product of this column with this column, and this column with this column, and this column with this column, you'll find that they're orthogonal. And when that happens, the symmetric matrix you get from A transpose A is really nice and easy to solve. So that's a very desirable quality, orthogonal columns. And that's going to come into play in the next section in chapter 4.4. See you then.